Good morning, physics students, one and all, and welcome to another episode of Physics. It's Mr. Finn coming at you, of course, from neighborly Northville. And I hope you guys are having a great day today. It is a Friday, at least I think it's a Friday, and we are studying waves. Now, the purpose of today, guys, is just to get you set up for future success. I got a few extra terms to discuss with you on the wave introduction. There's a few things we did not cover in one of our previous videos regarding things like nodes and antinodes, longitudinal types of waves versus transverse waves, and then, of course, interference, which could be constructive or destructive. Remember, guys, get to that Google form. Those forms on Fridays are available at 3 p.m. I want to try to get that done sometime before midnight, and then if your lab or whatever, get all your stuff done by Friday midnight. Because I try to sum up the weekly grades on Saturday mornings and get the participation scores in. So if you guys can do that, that would be awesome. Okay, guys, let's see if we can go to the board and get a little help on some of those extra terms. Okay, guys, helping us along the path today, let's take a look at a couple extra things that we did not discuss in one of our previous videos. The last time we had this up, we had a wave up here, which was transverse. So I'm going to stay with transverse just for a second, because that allows us to see a little bit more clearly some of the things we're talking about. So, what is an antinode or a node? A node is where the wave's amplitude goes to zero. In a transverse wave, points A, B, C, and D all are passing the equilibrium point. So if this was a wave on a slinky, it would be the point at which you could step over the slinky, if the slinky was moving sideways, where you would not see any motion at all. A lot of the displacement would be at the antinodes, which would be X, Y, and Z. X, Y, and Z are all antinodes, where the maximum displacement takes place. And A, B, C, D are all nodes, where no displacement takes place. So, even if a wave had a huge amplitude, you could exist on the wave very comfortably if you were at the node. So when you guys see your Tacoma Narrows bridge collapse, you'll see an example of a man walking down the bridge along the nodal line, because that's an area that does not displace. Should be able to do that pretty straightforward. Okay, now let's talk about what longitudinal waves are. Longitudinal versus transverse. Well, the only difference we said was longitudinal waves have amplitudes that move in the same direction as the travel, rather than at right angles. We can see that our transverse wave has an amplitude measurement that is perpendicular to the way the wave travels. But longitudinal waves, instead of crests and troughs, which we have in standard transverse waves, longitudinal waves have things called compressions and rarefactions. Rarefactions just means where there's elongation of those waves. So there's like large stretches without any pressure whatsoever, whereas these compressions are a lot of wavefronts banged up against each other. So compressions and rarefactions kind of take the place of crests and troughs, but it doesn't matter, because the difference between the middle of the compression and the middle of compression would still be called a wavelength. And the difference between the middle of the rarefaction and the middle of the next rarefaction, that would also be called a wavelength, and it would be the same number. Okay, so longitudinal waves are a little bit harder to visualize, but they're very important, as all sound waves are longitudinal. Okay, guys, one of our last things here is about interference. So what I've drawn here is I drew a brown line, which represents a standard transverse wave. That's the little bit bigger hump there. And I've also drawn right within it a purple line. Now, guys, for our sense and our purpose today, I've drawn the purple line at the exact same nodal pattern as the brown line, because I think it's a little easier to understand. But waves do not have to be this way. The nodes do not have to match up from one wave to they do or if they don't, no matter what, we get what's called interference patterns. Now, where the two antinodes of a wave match up together, that would be a lot of amplitude interference. That would be called constructive interference. So if I just added these two values together, what I would get is this pink wave. And that would be a constructive or overall addition of the two different waves we saw. But could waves add together so that there's no amplitude? Sure they could. One wave could have an antinode up here, and another could have a trough. If they met up, as long as those values were the same, the result would be zero amplitude. That would be called destructive interference rather than constructive interference. What I've drawn here for us is a constructive interference pattern where two wavefronts add together to give you a much bigger amplitude instead of a smaller or no amplitude. Okay, now it's important to know that constructive interference is not the term of resonance. We're going to come to that later. But resonance is a special kind of constructive interference that needs its own description. Okay, guys, that should just about do it for waves. Make sure you can get to practice the ideas of the differences between longitudinal and transverse. Although they both have amplitude, they both have wavelength, they both have frequency, they do not look the same. And certain waves can be one type or another. Sound waves, for example, are longitudinal, but light waves are transverse. So, let's just make sure we get a chance to look at that in some of our practice problems this week. Okay, guys, well, we have a very late day today as we have our Google form later on in the afternoon. But don't shortchange the waves section, guys. Waves actually is a very general type of topic, and it covers, it applies to chemistry, biology, physics, and earth science. So a lot of times you will see waves represented on some of those college entrance exams like ACT. So it's worth taking time to understand transverse waves, longitudinal waves, and all the little vocabulary and terms that go along with wave study. All right, guys, have a great day today, and I'll see you next week when we start talking about some other things in terms of sound. Take care now.